Welcome to today's paper reading. Today's paper is titled, Aya 23, Open Weight Releases to Further Multilingual Progress. This paper was published on the AR14 preprint by Viraat Aryabumi and colleagues from Cohere for AI. The Aya 23 model is a family of multilingual language models designed to serve 23 languages, reaching approximately half of the world's population. This model builds on the Aya model, focusing on depth rather than breadth by allocating more capacity to fewer languages during pre-training. Aya 23 demonstrates superior performance compared to previous models like Aya 101 and widely used models such as Gemma, Mistral, and Mixtral across a variety of tasks. To further the accessibility of these advancements, the open weights for both the 8B and 35B versions of Aya 23 are released. This work introduces Aya 23, a family of multilingual instruction-tuned language models supporting 23 languages. These models are based on Cohere's command model and the Aya Multilingual Instruction Style Collection. The majority of progress in large language modeling has been focused on English, leading to models that perform poorly in other languages. This has resulted in significant performance drops in languages not included in pre-training. The Aya 23 models aim to address these issues by improving performance in 23 specific languages. They balance breadth and depth, allocating more capacity to fewer languages during pre-training, which leads to significant gains over previous models. The Aya 23 models are released in two sizes, 8 billion and 35 billion parameters, with the 35B model achieving the highest results across evaluation tasks and languages. Figure 1 presents the multilingual benchmark results for Aya 23 models across 5 task categories derived from 8 datasets. The performance of Aya 23 models is compared against the massively multilingual Aya 101-13B and other widely used open-weight models of similar size, including Bacterian X7B, Gemma 1.1-7B IT, Mistral 7B Inst V0.2, and Mixtral 8X7B Inst. The results demonstrate that Aya 23 models generally outperform Aya 101-13B and the other models in the multilingual tasks evaluated, highlighting their superior performance in diverse linguistic contexts. Figure 2 presents the average win rates of Aya 23 models across 10 languages when compared to widely used open-weight models of similar size. This comparison highlights the performance improvements of Aya 23 over its predecessor, Aya 101, and other models like Gemma, Mistral, and Mixtral. The focus is on 23 languages that were included during pre-training, demonstrating Aya 23's balanced approach between breadth and depth in multilingual modeling. The Aya 23 model family is built upon the Cohere Command Series models, which are pre-trained using a diverse dataset encompassing text from 23 languages. Specifically, the Aya 23-35B model is a fine-tuned version of Cohere Command R. For these pre-trained models, a standard decoder-only transformer architecture is employed. This architecture includes parallel attention and feed-forward network, FFN, layers, similar to the Palm 2 model, which enhances training efficiency without compromising model quality, particularly in tensor parallel settings. Additionally, the SWI-GLU activation function is utilized, which has been found to offer superior downstream performance compared to other activation functions. The architecture also omits biases in dense layers to improve training stability and incorporates rotary positional embeddings, ROPE, for enhanced long-context extrapolation. A byte pair encoding, BP, tokenizer with a size of 256K is used, which performs NFC normalization and splits digits into individual tokens. This tokenizer is trained on a balanced subset of the pre-training datasets to ensure efficient language representations. All base models are trained using the FAX framework, a JAX-based distributed training system on TPU-v4 chips, employing a combination of parallelism strategies to maximize training throughput. Table 1 provides detailed architecture parameters for the Aya 23 model family, which includes models with 8 billion and 35 billion parameters. Key parameters include embedding dimensions, FFN hidden dimensions, and vocabulary size, which are crucial for understanding the model's capacity and performance. The table highlights the differences in these parameters between the two model sizes, indicating the trade-offs between model complexity and computational requirements. In this section, we discussed the fine-tuning process for multilingual models. The data used for fine-tuning includes several sources: multilingual templates, human annotations, and translated data. The multilingual templates consist of 55.7 million examples, covering 23 languages and 161 datasets. Human annotations provide 55,000 samples, curated by native speakers in 23 languages. Translated data includes 1.1 million examples, sourced from widely used English datasets translated into the languages we train on. Additionally, synthetic data is generated using prompts from ShareGPT-5 and DALL-E 15K, resulting in 1.63 million examples. The training process involves 13,200 update steps with an 8192 context length, using the Atom optimizer with a cosine schedule learning rate. Table 2 presents an example of a prompt completion pair formatted in a chat style for the IA-23 models. This format uses special tokens to clearly indicate the roles of the user and the chatbot, as well as to delineate the turns in the conversation. This example serves as a demonstration of how the IA-23 models handle instruction tuning and inference using this structured chat format. Table 3 provides an overview of the datasets considered for evaluation. It categorizes tasks into unseen tasks and seen tasks. The unseen task category includes 4 discriminative tasks that were entirely excluded from training, along with multilingual MLU. The seen tasks category refers to generative tasks where supervised training was performed, with instances held out for validation and test splits. The evaluation languages are limited to 24, except for the first 3 datasets, X-Winograd, Scopa, X-Story Close, which use all available languages. The evaluation framework for the models includes several key tasks. For discriminative tasks, the models are assessed on completely unseen tasks such as X-Winograd, Scopa, and X-Story Close, using zero-shot evaluation. Additionally, general language understanding is tested using multilingual MMLU, which is evaluated in a 5-shot setting. Multilingual mathematical reasoning is evaluated using the Multilingual Grade School Math benchmark. For generative tasks, performance in machine translation and summarization is measured using Flores 200 and XLSUM datasets. Preference evaluation includes both LLM simulated win rates and human evaluation on the DALL-E machine translated and DALL-E human edited test sets. Safety, toxicity, and bias are evaluated using adversarial prompts from the Multilingual ADV bench and toxicity measurements with Perspective API. Table 4 presents the zero-shot performance of various models on discriminative unseen tasks, specifically Scopa, X-Story Close, and X-Winograd, across multiple languages. The IA-23-35B model leads with an average accuracy of 70.8%, surpassing all other models. Within its size class, IA-23-8B achieves the highest average accuracy at 67.6%, outperforming models like Gemma 1.1-7B and Bactrian X7B. Mixtral 8X7B Instruct V0.1 also performs well with an average accuracy of 68.8%. These results underscore the effectiveness of IA models and multilingual discriminative tasks. In zero-shot performance, IA-23-35B achieved an average score of 70.8%, outperforming all baselines, including Mixtral 8X7B. IA-23-8B also excelled, achieving the best score within its class. For the multilingual MMLU, IA-23-35B again outperformed Mixtral 8X7B with an average score of 58.2%, while IA-23-8B scored 48.2%. In generative tasks, IA-23-35B achieved a SP Blue score of 40.4, significantly higher than Mixtral 8X7B's 32.6. IA-23-8B also performed well with a SP Blue score of 37.2. Table 5 presents the multilingual MMLU, 5-shot, results for various models across 14 languages. IA-23-35B leads with an average score of 60.3%, outperforming all other models. IA23-8B, despite being in a smaller model class, achieves the highest average score of 57.5%, highlighting its strong performance. Mixtral 8x7B Instruct v0.1, another notable model, averages 50.2% across the tested languages, showing competitive results in the multilingual evaluation. Table 6 presents the Multilingual Grade School Math (MGSEM) benchmark results for various models, focusing on the IA models and their performance against baselines. The IA23-8B model achieves an average accuracy of 48.2% across all languages, performing best among comparable smaller models. The larger IA23-35B model outperforms Mixtral 8x7B Inst on average with a score of 58.2% versus 57.1%. Notably, IA23-35B shows significant improvements in non-European languages like Arabic, Hindi, and Vietnamese, scoring 12.1%, 10%, and 6.5% higher respectively. This table highlights the strong mathematical reasoning abilities of the IA models across multiple languages. Table 7 showcases the translation and multilingual summarization results for various models. IA23-8B leads with a SP Blues score of 37.2 and a Rougel score of 27.5, outperforming other models in its class. For larger models, IA23-35B achieves a SP Blues score of 40.4 and a Rougel score of 30.9, significantly surpassing Mixtral 8x7B in both translation and summarization tasks. Table 8 presents the results of human evaluations in terms of win rates for pairwise comparisons between various models. Notably, the IA23-8B model achieved a 50.8% win rate against the IA101-13B model, and the IA23-35B model achieved a 57.6% win rate against IA101-13B. These results indicate that the IA23 family of models consistently outperforms the IA101-13B model across all evaluated languages, highlighting the significant impact of a stronger pre-trained model. Figure 3 presents the LLM as a judge evaluation results, showing the win rates for IA23 models compared to similar-sized models across 10 languages. The evaluations were conducted using GPT-4 Turbo as the judge LLM. Notably, IA23 models achieved superior win rates, especially in non-European languages such as Turkish, Hindi, and Japanese, demonstrating their effectiveness in diverse linguistic contexts. Table 9 presents the results of the Multilingual ADV bench, detailing the percentage of harmful responses generated by different IA models when prompted with multilingual adversarial test split prompts. The responses were judged by GPT-4, with a lower percentage indicating better performance in terms of safety and toxicity. Notably, the IA23 models, including IA23-8B and IA23-35B, exhibit significantly reduced rates of harmful responses across 6 languages compared to the previously benchmarked IA101-13B model. This improvement is particularly evident in languages like Arabic and Italian, suggesting enhanced cross-lingual transfer capabilities in the larger IA23-35B model. The table underscores the need for continued safety alignment in multilingual fine-tuning stages, as the current scores reflect the extent of alignment required for specific safety cases captured in ADV bench. Figure 4 presents a toxicity analysis of IA models, specifically IA101, IA23-8B, and IA23-35B, when prompted with sentences related to identity groups such as gender, ethnicity, and religion. The analysis evaluates the expected maximum toxicity and toxicity probability of the model completions. It is observed that both IA23 models generally exhibit lower expected maximum toxicity and a lower toxicity probability compared to the IA101-13B model, with the exception of English prompts where the toxicity is slightly higher for the new IA23 models. Figure 5 illustrates the prospective API toxicity scores for the IA101, IA23-7B, and IA23-35B models when generating responses to prompts about racial identity groups in English. The data reveals that the IA-23 models tend to produce less toxic descriptions for Asians and Latinx individuals. However, these models exhibit a higher likelihood of generating toxic descriptions for Black and white individuals, particularly when the descriptions are about women. Overall, the IA-23 models generally demonstrate lower toxicity scores compared to the IA-101 model, indicating an improvement in handling sensitive topics related to race and gender. The authors introduced the IA-23 family of multilingual models, which have demonstrated high performance across various multilingual benchmarks and human evaluations. By releasing these model weights, they aim to contribute to future research in this area. However, they acknowledge significant limitations in coverage, as the models are currently focused on a subset of 23 languages, which represents only a small fraction of the world's linguistic diversity. Specifically, there is an underrepresentation of languages from Asia and Africa. Future work will focus on improving both coverage and performance, developing tailored language models, and addressing cultural and linguistic nuances to ensure more equitable language technologies. Thank you for watching.